free body diagrams, I said that we could write weight as mg. And weight was a force. M was our mass, and g was our acceleration due to gravity. This acceleration due to gravity is around 10. It varies a little bit. And I said later on we'd see where this came from. Well, I'm going to show you now where this constant comes from. So it turns out that anything that has mass exerts a force on anything else that has mass. So whether you're there or you're there, you are feeling a force that is pulling you towards the center of the earth. And you're probably all familiar with that story of Newton and the apple, which is probably apocryphal. And it wasn't that he realized that gravity pulled the apple down. It was that he realized that the same thing that pulled the apple down was keeping the moon going around an orbit of the earth. And this is gravity. So Newton's universal law of gravitation. This is given as F with a big G is equal to G M1 M2 over R squared. G is a universal constant. It's 6.67 times 10 to the negative 11th meters squared divided by kilogram squared. M1 is going to be the mass of one object, M2 is the mass of the other, and R is the distance between their centers. So if we're looking at our previous picture, our R is going to be this distance, which is typically, if you're on a planet, the radius of the planet, because you're not really going to affect that much. It's the absolute value of this because if we're talking about the force on me from the Earth, it's pulling down. And if we're talking about the force of, sorry, I said it backwards. The force of me on the Earth is pulling the Earth up, and the force of the Earth on me is pulling it down. Those are equal forces in our opposite directions. So this is going to give us a magnitude. So everything affects everything else. It just turns out that you have to have something that's incredibly massive for this to matter. We talked about what the forces are. Gravity is by far the weakest. That's one of our big problems. Some evidence of this. We know that we put satellites up at certain speeds, they'll move in circular orbits. We know the tides. So we know that the tides are affected by the moon and by the sun. And this effect is causing the moon to slowly drift away. So these are going to be equal and opposite forces. So the Earth is going to pull on the moon as much as the moon pulls on the Earth. The Earth's going to pull on me as much as I pull on the Earth. Why are they not affected equally? Because their masses are so different. And we'll get into center of masses in a later thing. But yeah, it's a distance between the center of masses is what going to be what our distance is. All right, so I said that anything with mass attracts anything else with mass. So if you think about two average size adults, 75 kilograms, like 165 pounds, they're about a meter apart. The force between them would be about 3.7 times 10 to the negative 7th newtons. A penny in your hand would be about 67,000 times heavier. So you can see how small this is on the grand scheme of things. All right, so how do we get G? So if we look at our two equations, which I'm saying are the same, I'm going to make this the mass of the Earth. I'm going to make this the mass of me. So if we look at this, if we cancel out these m's, we get what G is. And so if I know what the universal constant is, the mass of the Earth, and how far I am from the center of it, I can figure this out. So I just plug in the 6.67 times 10 to the negative 11th. The mass of the Earth is 5.98 times 10 to the 24th. And the average radius of the Earth is 6.36 times 10 to the 6 meters squared. And I get 9.8. Which they did the same thing in your book to find out what the mass of the Earth is, knowing what little g is and the radius of the Earth. Although they use 6.38, I always use 6.36. All right, so this varies based on two things. It's based on your altitude. So the further you are, the less gravity you're going to be. So if you are at the top of a mountain, it's going to be less than if you're at sea level. And it also is affected by how fast you're going around the Earth. If you're at the equator, you're going to be going faster, and you're going to have that fake force that you feel like is pushing you out. Well, that's going to work against the acceleration due to gravity. So if we're at the equator, we're going to have less, even though we're at an elevation of 0, because we're moving faster. The North Pole is also at an elevation of 0, and look how much more it has of gravity, because if you're at the North Pole, you're barely spinning around. Somebody at the equator is going 1,000 miles an hour, and if you're right at the North Pole, you might be going, hundreds of miles an hour. And it also turns out that as you spin something, it will bulge, which I'll show you guys in class in a demonstration. So as we spin something around, the center of it bulges. But the Earth is not round. The Earth is roundish based on that. So if we get the right speed to put something in orbit, we can figure out what this is based on what the gravity is. And we just have to be able to maintain the speed, and that object can be in free fall around the body. So that's why people on the space station are floating. There isn't no gravity up there. They're in free fall, just like the people in the Vomit Comet. So you would just need to find out what that was. Based on our two equations, right? We have our universal law of gravitation, and we have our centripetal force. We can cancel out the satellite, and we can cancel out one of the r's. And so what does our velocity need to be? It needs to be the square root of g times the mass of the Earth divided by how far we are from the center of the Earth. So this is going to be our radius plus our elevation. And as long as you maintain that speed, you'll be in free fall and not get closer or further away. And satellites typically have ways of maintaining their speed, gaining a little bit or losing a little bit. So the speed itself keeps it from the Earth, and it keeps moving around. This would be the same if you were in a very tall building and your elevator cable were to break. You would feel like you're in free fall. I told you guys about the demon drop, which was just a thing that dropped you straight down. And you could see through the bottom of the cage. You would sit down, people would put pennies on their knees. And then as you drop down, you could see the penny would float up just a little bit, and then it would just stay there as it was in free fall down, weightless as it went down. If we're going up at a constant velocity, our weight is equal to mg. Remember, not moving or constant velocity is the same situation. We can't tell the difference. If we are accelerating up at 5 meters per second squared, we're going to feel like we weigh 1.5 times as much. All right, a man weighs 100 or 1,000 newtons on Earth. He goes to a planet with half the radius and the same mass. What is his new weight? So, looking at our formula, I'm going to put in ones for things that don't change. Universal gravity doesn't change. The man's mass doesn't change. The mass of the planet doesn't change. The radius went from 1 to 1/2. So I have 1 divided by 1/2 squared, which is 4. So he would weigh 4 times as much. So he would be a 4,000 Newton man. A satellite of mass M moves in a stable circular orbit around a planet of mass big M. What is the radius of the satellite's orbit? So if it's circular orbit, it is F net equals mv squared over r. We have our satellite. What force is keeping it in orbit? It would be gravity going right down towards the center of the planet. So this would be G, big M, little m, over r squared equals mv squared over r. I want to solve for r. I'm going to cancel out little m and 1r. I'm going to multiply this r to that side, and I'm going to divide by v squared. And it looks like our answer is this one. Both of these, the previous slide and this slide, were AP multiple choice questions. All right, so we're to the end of our chapter. So we have 4 fundamental forces, and I talked about this in the beginning. We have gravity, we have electromagnetism, and we have the weak nuclear and the strong nuclear. All of the other forces, friction, normal force, tension, are really electromagnetic forces interacting. So here, you never really touch anything. You're not sitting in the chair you think you're sitting in right now. It's just that the electrons on the chair are getting really close to the electrons on you and pushing off, and nothing ever really touches. What we feel as touching is this interaction of these negative charges. Even if you cut a piece of paper with scissors, it's the charges on the scissors are pushing the charges on the paper apart. All right, so we have a special word for if something's moving at a constant speed in a circle, and that is uniform. This is good because that's going to allow us to use mv squared over r. In circular motion, we have a center-seeking acceleration, which we call centripetal acceleration, which is AC. Circular motion requires a centripetal force, so a force towards the center. Something is not going to turn unless you make it turn. Its tendency is to not move, or if it's moving, to continue in a straight line. The centripetal force can be provided by all sorts of forces or the combination of forces. We have Newton's universal law of gravitation. This gives us a magnitude. That's why it is the absolute value, and that's because the same equation would give you the force between the two masses, and you need to decide the direction. I am pulling the Earth up. The Earth is pulling me down equally. Satellites stay in orbit because they're going fast enough to just be in free fall. And so we found the value of that.